So before I get started, and please don't penalize me for this, Will, I just wanted to give a big shout out to Will himself. So we spun out as a company in 2022, almost 3 years ago. So we were a team at Google X. And Brain, I had a kind of informal relationship with Will that eventually became a great kind of friendship and partnership. And actually, Will is tied for being our first advisor ever as a company. So big shout out to Will, and great to be here and talk about all that what we're doing. Yeah, super excited to talk about thermodynamic computing together and what we view to be as kind of the next frontier for silicon supremacy. So I think we all know that right now we are in sort of global AI race. This year we'll put up another 300,000 GPU clusters. We are starting to train models in a way that's actually distributed across data centers. And in the next 5 years, we'll need to have gigawatt data centers to enable scaling some of these runs, potentially another 10,000x. Kind of by definition, to stay ahead in this race, what we're looking for is innovation momentum, which means predictably being able to improve our AI capabilities in some way. And for this reason, we like to look at so-called scaling laws. So scaling laws basically tell us that in exchange for more compute and a certain amount of data, we can kind of know how much our models may improve. And really right now, we are very much so still in a good time for scaling laws. So for LM pre-training, there's still kind of significant opportunities that we foresee over the next few years. We've really, just to give a sense of some of the other potential opportunities, there's like 2 orders of magnitude more data that's available in terms of tokens and other modalities like video that we've barely started using. And so in turn, the semiconductor industry has essentially rewired itself to power these kind of scaling laws. And this goes beyond just having kind of denser compute or more parallelism. We're solving fundamental problems when it comes to kind of memory bandwidth and also interconnects. And so, bigger KV caches mean better reasoning models. And so now we're doing things like stacking high bandwidth memory taller and taller. We're moving to chiplets, multi-die architectures. There's still a ton of innovation that's kind of happening on the semiconductor side right now for us to continue to hit these scaling laws over the next few years. Then we kind of look ahead at the future. So when we think about sort of the next opportunities in terms of AI scaling laws, I think we can all agree that the reason we're in this race to build AI is not so we have a partner to do homework problems or write better emails, even though that's great. I think where we're starting to agree, some folks may have heard it from Jensen at GTC, or as one of the rare areas where the AI godfathers actually agree, kind of the next frontier for AI is AI that is able to, in some way, natively understand the real world, right? And this opens up some of the most exciting applications by far. So when we think about like designing better hardware or even chips themselves, when we think about sort of autonomous transportation, when we think about real calibrated reasoning that goes beyond the heuristics we have today, these are the kinds of algorithms that we're talking about that we're super excited to scale in the future. And so I think the natural follow-up question to that is, do we have kind of clear scaling laws for these algorithms right now, and sort of how are they performing, and what does it mean for the state of compute right now? And certainly we don't have the kind of detailed answers to all of these questions, but there is a sense in which the order of magnitude of compute that's required to train models, like for video diffusion or kind of in Bayesian machine learning and some of these other important kind of frameworks that were mentioned, that we are hitting some sort of significant wall right now. But what's very interesting is when we actually look at these algorithms, and try to write them down, they all fit within this, many of them fit within this nice kind of consistent framework of simulating thermodynamics, right? So in other words, kind of solving Longevin's equation. So that's just kind of a first observation that some folks in the community made in the last few years. And so when we look back and compare to quantum, many people are familiar with the idea that when we think about the sort of conceptual underpinnings of quantum computing, there is some attribution to Feynman quote, for example, where he mentioned, if you want to build a simulator of nature, then it better be quantum mechanical. But for these kinds of AI algorithms that we're talking about here, there is no kind of material, like quantum effects are not necessarily relevant. And when we think about in our own kind of day-to-day, in terms of our interactions with physics, most of the time quantum is not really relevant. When we think about most algorithms like diffusion that are actually, in terms of physics-inspired algorithms that are actually useful, quantum is also not really relevant. So I guess a caveat which I would add, and that we're trying to add in addition to Feynman's quote, is if you want to build a simulator of nature, then it better damn be thermodynamic almost always. Okay, and so the kind of trillion-dollar follow-up is, could you build a computer which actually simulates these equations much faster than with GPUs and sort of today's paradigm? And to answer this question, we might actually look to thermodynamics for some principles as far as how it could be done. Many people are familiar with the idea of Landauer's limit, which gives you a sort of infinite time limit as far as energy consumption. And there's a sort of analogy for engines and refrigerators, which we may allow to operate arbitrarily slowly, but they're super energy efficient. But obviously with AI algorithms, speed is very important. So we want them to be fast. So we're not really looking at Landauer's limit, but some kind of finite time treatment of thermodynamics where given a target speed or time budget that we want to hit, there's some kind of energy limit that we could seek to meet in this context. And the way to think about it, there's actually a conceptual way to think about what we're trying to do in this kind of device, which is that usually we're kind of fighting noise and dissipation in computers we have. So in terms of transistors, dissipation is a big kind of punishment that we have as we miniaturize. But what if we were able to actually morph that dissipation into useful noise in terms of morphing it into the distributions that we're actually trying to sample? And so some of the equations here give you a sense of different kinds of lower bounds in terms of Wasserstein distances and things of that sort. And so I would say that doing this is incredibly well motivated. In my opinion, still very much so under-discussed. And I think it's great that at this conference we call it Physics Tech, kind of widening to kind of include other emerging technologies beyond quantum, because it's kind of clear in our view that this is at the minimum a path for achieving new scaling laws beyond 2030. There are other possibilities too, like this could be the true, I hope Ilya's not in the audience, but this could be the true kind of straight shot to superintelligence in terms of kind of a more direct path. We also, when we look at some of these plots in terms of the implied kind of performance to power ratios, we literally end up off the chart, so outside of the sort of tunnel that we're stuck in today with today's paradigm. We have a bunch of publications which sort of touch on also asymptotic results. Okay, and now lastly, how do you build it? So for the last 6 or 7 years, academic groups, many of which we work closely with, have tried to build computers like P-bits, scale them up and put them in ASICs. There are some real challenges that sort of come up as you try to build a thermodynamic computer, many of which we've been focused on solving for the last few years since we spun out of Alphabet. And what it boils down to is kind of building an architecture which is obviously precise, also expressive, so that way you can represent non-Gaussian distributions, other kinds of complex probability distributions, and also being able to handle connectivity well as you kind of scale up these sorts of devices. So many parallels with quantum in that sense, where in the end, scaling is really kind of the key challenge when you think about thermodynamic computing, and so that's been a serious focus for us. So we have our first design, which we call Carnot. And right now, the kind of performance metrics are super promising. We're doing this at a pretty small scale right now. But when we look into the future, again, a lot of kind of what we're doing does come back to kind of scaling. And so now, some of our partners are receiving sample silicon from us. We are also delivering our software in terms of some of the EDA tools we've developed to design these kinds of ASICs and also some of these kinds of physical AI models that I mentioned. When we look into the future on the partnership roadmap, there's a few things that are kind of top of mind for us. So one is starting to establish the real kind of industry standards for thermodynamic computing. All right, and that's it. Thank you.